Welcome back to Prima Executive Gathering 2025. Ladies and gentlemen, after a quick coffee break session, I hope everyone had a great time experiencing the Prima Hub Nusantara. And with this high spirit, let us welcome the next session. It's a race against post-quantum cryptography, evolving threats, advancing solution. And we are honored to have Mr. Neil A. McEvoy, Vice President of Special Projects of FIM, to lead this session. Ladies and gentlemen, please give a big round of applause welcoming Mr. Neil McEvoy.
Well, thank you very much, ladies and gentlemen, and I want to, first of all, give my appreciation to all of you and the organizers especially for inviting me here to speak with you. It's really a great honor and privilege to be flown all the way from London to address this special audience. So thank you very much indeed. I'm really impressed by the setup here. I've never spoken on a stage as big as this, I don't believe. I think I will also get my 10,000 steps of exercise while I'm speaking with you. So I hope in the next 45 minutes or an hour that I can repay the respect that you've shown me to invite me here. Okay, let's get on with things. So this is what I'm going to speak to you about. First of all, I am going to talk to you a little bit about quantum mechanics and the concept of a quantum computer. I promise that this is not going to be terribly technical. You're not going to see any mathematical equations. But it's really interesting. I hope you will find it interesting. And we kind of have to go there to explain why a quantum computer is different to the normal computers that we use every day and that we're carrying around with us in the form of our phones and tablets and PCs and so forth. Totally different thing with different properties. I'm then going to make some predictions. James already made one, and thankfully my predictions are kind of roughly in line with his, about how quantum computers will develop and about when they will become relevant to us in terms of being able to crack the codes that we're using today to protect our communications. Predictions are really, really difficult. We'll get on to that. So it's my opinion, right? It's not an absolute forecast of the future. I can't say that it will rain tomorrow or whether it will be the day after. But for what it's worth, I'll give you my view. And then we'll talk about how to get ready for this event. You know, at some point, a quantum computer will be able to crack those codes. What do we need to do to get ready for that? And actually, it's quite a lot. And as James was saying, the amount of preparation that we're going to have to put in is probably roughly the same time scale that the quantum computers will develop to where they need to be to break our codes today. So the time to start thinking about this and to start planning is now. Maybe start thinking this year, start planning next year. So just a little bit about my background, where I kind of come from in my career, which will help me to understand why I know a little bit about this subject. I started out my career academically doing research in quantum mechanics at Oxford University, trying to explain why certain classes of novel chemical compounds had the shape that they had and interacted it with light to produce spectra, why those spectra had certain properties. And sometimes those things were surprising. They appeared to be anomalous. And I would do calculations in quantum mechanics to help to understand why those compounds had those properties. So that's a very long time ago. When I left Oxford, I started working for a space and defense contractor in the UK in communications and computing, software and hardware. And the middle picture is quite important to me. And the picture is of a spacecraft which is called Giotto, which was launched by the European Space Agency. And in the background is Halley's Comet, which came around close to Earth in 1986. And my job was to devise some codes which would hopefully ensure that data that was collected from Halley's Comet by the spacecraft would be transmitted back to Earth and be decodable at the time it got to Earth. Now, this was a really difficult problem because nobody knew what the electromagnetic environment of a comet would be. So, one would think that there would be some interference on the radio signals carrying the data that we were sending back to Earth, but the nature of that interference we didn't know. So I was devising codes really to try to cope with almost any possibility. Of course, after that mission, this was a European mission, there were Japanese and Russian and American missions too. Afterwards, of course, a lot was known about the electromagnetic environment, and it turned out to be quite benign. So my solution was over-engineered, but at least it worked. Because if it hadn't worked, then the project would have been set back by 76 years, which was rather a long time. Now, believe it or not, that project, or the subject of that project, is relevant to what I'm going to talk about, and we'll get to that. Later on, I started my own company, Consult Hyperion, in the mid to late 80s, and Consult Hyperion was acquired by Theme a little over a year ago. So we're now one company. We always operated in the same areas of digital payments and smart mobility and digital identity. Theme concentrating mainly on the testing and certification side with some consultancy. And Consult Hyperion, as the name suggests, being more the consultants, the designers of systems, with a little bit of testing and certification as a sideline. So putting the two companies together made, a huge amount of sense. And now we think we've got a kind of great end-to-end offering throughout the life cycle of projects. Mostly what we have been doing in Consult Hyperion, or what I've been doing in Consult Hyperion, has to do with financial cryptography. So applying cryptography to financial transactions to make sure they're confidential where they need to be, and that they have integrity, and that people can't repudiate the fact that they issued instructions from A to B. So most of my career, that's what I've been concentrating on. Now, for me, pretty well near the end of my career, what's really exciting is that I can now go all the way back to here and apply my knowledge of quantum mechanics to financial cryptography. And so, that's what I'll be talking about today. So I'm really, really pleased about that. But this is going back an awful long way for me. So in the last year or so, I've been having to do a lot of revision from what I was doing at university to kind of get quantum mechanics back into my head. It's enough about me. So let's talk about quantum computing, and here is a quantum computer, okay? So it's not going to fit inside my MacBook Air, all right? It's quite a big thing, and you need a lot of apparatus in order to control something that ultimately is very, very small, because quantum mechanics is all about how really, really small things like atoms and molecules and electrons and protons, photons, how they behave. And you've got to be able to control them at that minute scale in order to be able to do computations with them. So the core of a quantum computer is absolutely tiny, tinier than you can really imagine. But in order to keep it under control, you need a lot of apparatus. And this isn't really showing all of it either, because a quantum computer has to be kept separate as far as possible from its surroundings, because any amount of interference from outside is going to change things. So this means that quantum computers are generally very, very cold at the core, a tiny fraction of 1 degree above absolute zero. So basically, you need a very efficient refrigerator. And you also need to keep a quantum computer isolated from mechanical interference. So even the smallest vibrations can change the state of a quantum particle, which is going to throw out your calculations. So they're big things. They will get smaller, but we'll get onto that in more detail. Okay, so I'm going to get a little bit into quantum mechanics. This is Richard Feynman, who was one of the early pioneers of quantum mechanics. Not one of the founders of quantum mechanics, which were people like Schrödinger and Heisenberg and Dirac, who you may have heard of, and a little bit of Einstein thrown in as well. But Richard Feynman was taught by those people, and also in the next wave, who really helped the world to understand what the ramifications of quantum theory would be, and ultimately enabled the microprocessor revolution that has given us our laptop computers and mobile phones, etc. And you can read what he said. If you think you understand quantum mechanics, you don't. So it's kind of really complicated, but more than that, it's really, really weird, okay? And I'm going to introduce you to some of that weirdness. And there's kind of a reason that it's weird, and it's because we're looking at the behavior of minute things that we can't sense. You know, our eyes can't see an atom, our ears can't hear them, we can't directly touch them, or at least distinguish one atom from another. And our languages have evolved to describe those things that we can sense directly, like plants, animals, footballs, and automobiles, okay? Now, if I were to talk to you about how I would kick a football and it would arc over to the other side of the room, and Newton's laws of motion, you'd kind of understand a lot of that intuitively, and we have the language to describe it. So some results of Newtonian mechanics are maybe a little bit surprising, but at least we can understand what's going on by using our natural languages. We can't do that with quantum systems. So what we have to do is to construct analogies to say, well, it's a little bit like, okay? And that can help understanding. But like all analogies, they eventually break down. So it's just the analogies are just an aid to help you to think, but they're not really a complete description. The mathematics is a complete description, and you'll be glad to know that I won't go into the mathematics. So I'm going to talk to you about 3 properties of quantum systems. So a quantum system, let's call it an atom, can only exist in a finite number of states, okay? So if I have a ball and I kind of kick it across the room, then it's in an infinite number of places in its journey, okay? But a quantum system can't be in an infinite number of places or in an infinite number of states. Going back to the ball, you know, it can travel at a certain speed, and that's an infinite continuum of different speeds. It will obviously slow down as it gets to the other side of the room, and it will slow down gradually. Quantum systems jump from one state to another. Now, one of the weird properties is this thing called superposition. There is a quantum property that's very important, which is called spin. And it's called spin because it's analogous to a spinning ball or a spinning coin. And a quantum system that's spinning can be in one of two states. It can be spinning in one direction or another direction. The analogy with spinning is good because a lot of the mathematics that describes spin in a quantum sense is the same as described spin in a macro sense. And in particular, the law of conservation of angular momentum applies to quantum spin just as it does to the spinning of large objects. But a quantum system can only be in one of two states, it's normally described as plus 1/2 or minus 1/2 for reasons that I won't go into, but you can think of it as 0 and 1 in a binary computing sense, or in a coin, you can think of it as heads and tails. Now, if I spin this coin, thankfully I caught it, then it's come out tails, okay? Spin it again. I get tails again, so it's at random. Eventually I will get a head, and if I do it often enough, it'll be roughly the same number of heads and tails. So when I've caught it, and when I'm looking at it, it is definitely tails, okay? And if it were the other way around, it would be definitely heads. There's no in between. So that's a little bit like quantum states. When it's in midair, is it heads or tails? Well, it's neither. Or you could regard it as being a combination of both. And that's a little bit like quantum particles. So when it's kind of neither, when you're not directly looking at it to try to determine what spin it has, then it can be any combination of both. Imagine the coin. At any one time, if you take a photograph using a precision camera, then it might be sloped like that. And you might say, well, it's 80% heads and 20% tails. Or it might be the other way, and you could say, well, that's 70% tails and 30% heads. Now, actually, there are an infinite number of superpositions. They're called linear combinations. But as soon as you look at a quantum particle, like when I've caught the coin, then it is going to be one thing or the other, a 0 or a 1. This is very important in quantum computing. So on direct observation, the terminology is that the system will collapse into one state. Now, this is a really weird one, entanglement. So that means that you can have two quantum particles that are separated, and providing they were once together and they've been created in the same process, finding out about the state of one system will tell you about the state of the other, okay? And when I find out about one system, it will have collapsed into one state by the act of looking at it. Entanglement turns out to be very useful in terms of communication. So that means, for example, if I can create two photons, two particles of light, if you like, in one process, and send one photon in one direction and another photon, the other photon in the other direction. And you could do this across the world if you had a fiber optic cable long enough. Then if the person over here says, oh, okay, well, it's tails, then because of the law of conservation of angular momentum with spin, the guy over here will know that it's heads. And this is a way, his one is heads, and this is a way of sending information potentially over great distances. The engineering is difficult, but potentially over great distances, defeating an eavesdropper. So this is a potential way to transport keys from one place to another in a way that can't be interfered with. So you don't often read about that in treatments of quantum computing or quantum cryptography, because this is a kind of a separate thing. This quantum process helps the good guys, okay? Most of what we'll be talking about today is quantum cryptography used by the bad guys in order to discover our keys. This is a way of staying ahead. And then there's interference. I've talked about quantum systems sort of mainly as particles, okay, discrete particles. But a quantum system is also displays some particle-like properties in certain circumstances, but in other circumstances, they display properties more like a wave. It could be a water wave or a sound wave, a light wave, whatever you want. They behave like waves. In reality, they're neither particles nor waves, but the analogies help. What they are in reality is a wave function, which is a complicated mathematical function that is able to describe their behavior. Now, has anybody heard of the double-slit experiment? Any physicists, chemists in here? No. I'm not going to describe it because I think it would take too long. But what it proves is that a single quantum system can interfere with itself. That's the very weird thing. Normally when we talk about interference, if you imagine dropping two pebbles into a pool, then each will create a wave, and they'll radiate out in circles. When those circles eventually intersect, then you'll get a complex pattern of peaks and troughs. So with a peak, the signal is reinforced. With a trough, it disappears. So this is what we mean by interference, and quantum systems demonstrate it. And weirdly, a single particle can interfere with itself. So what does all this mean in terms of quantum computers? Well, they exploit all three of these properties of superposition, entanglement, and interference. And we have something in quantum computers called a qubit, analogous to a bit, which is a 0 or a 1 in the classical computers that we all deal with. All the computers we have are called Turing machines, after Alan Turing, who first developed the theory of computing in the 1940s. A quantum computer is not one of those Turing machines. Now, a qubit can represent a 0 or a 1, just like a bit, but because it's exploiting superposition, it can be everything else in between. And what that means in practice is that if you are able to design a machine which can operate on a qubit, on a quantum system, then in effect, you can do an infinite number of calculations at once, okay? Which is helpful in solving certain mathematical problems, including the mathematical problems that we use to construct asymmetric keys in our cryptography. So doing that is one of the classes of problems which quantum computers are going to be good at. There are a few others as well. And I should say that what they threaten is the asymmetric algorithms. And these are the algorithms which we use today in financial systems in order to establish a different type of key, a symmetric key, that protects the individual transactions. Now, those symmetric algorithms are not vulnerable to quantum computers, okay? It's just the asymmetric ones. And the asymmetric algorithms are also used to give us our digital signatures so that we can tell a message has not been interfered with as it moves from A to B. And further than that, we can tell who it came from, and they don't have the possibility of denying that it came from them because it must have used their private key, which it is their responsibility to look after. So technically, it's asymmetric algorithms and keys that are at risk, and practically what's that's used for in our world is for distributing other sorts of keys and for doing digital signatures. So that's what we have to bear in mind. So qubits can be entangled, and I already mentioned one advantage of quantum entanglement for us is that theoretically we can move information a long distance whereby A and B can be absolutely certain they know what the information started out as, but somebody attempting to eavesdrop can't. But also quantum entanglement is used in quantum computers, and it's used to construct logic gates which perform the mathematical operations on the qubits. So we have gates in microprocessors. They're called things like AND gates or XOR gates that do very, very simple operations. Constructing those simple operations for a quantum computer is actually quite a difficult engineering problem, but it can be done and it is being done. And qubits demonstrate quantum interference. This is really important for the calculations, because what it means is that the correct results emerge in an interference pattern. So where there is a bright line, that's constructive or positive interference, and that's coming because the correct paths have been followed, indicating what the result should be, or in our case, kind of indicating where you started from. So for example, if you have a key that's the product of two very large numbers, which are prime numbers, then an interference pattern ultimately will tell you these are the prime numbers that were started from to construct that key. Now, it's more complicated than that. It's not a single step. But the interference patterns are tremendously useful because where there is no bright line indicating positive interference, where there's been destructive interference, this means that the potential starting point can be ruled out, okay? They didn't begin from there when they were constructing that key. So all these three quantum effects combine together in a quantum computer to enable certain classes of mathematical problems to be solved, including the ones that are important to us, which is breaking our symmetric cryptographic keys. So where are we today? And quantum computers started out as a theoretical concept around the time I was doing quantum mechanics, which was in the late 1970s and early 1980s. So somebody realized that quantum mechanics being what it is, that, hey, actually, you could construct a computer. And that was just an academic thing for a very, very long time until the last, I'm not even sure, but 10, 15 years, people began to construct in the laboratory extremely primitive quantum computers to demonstrate feasibility. They were of no practical use whatsoever, but it was shown that the concept was real and engineering existed which could implement one. Where are we up to today? Well, we can, I say we, not me personally, computers can be constructed, quantum computers, of around about 1,000, 1,100 qubits. And as we'll see, that's not nearly enough to break the standard of keys that we're using today. But from 10 years ago, a couple of qubits to 1,000, that's quite good progress. So that's where we are today. I'm now going to start with the predictions. This man wasn't nearly so clever as Richard Feynman. In fact, he was well known for saying kind of paradoxical things unintentionally, including this one. It's tough to make predictions, especially about the future, which of course is the same thing. And there's no exception here, okay? So what you will hear from me is a personal view. There's a big error bar. I could be wrong in either direction. But I think most people who have studied this and commented on it, I'm not so very far from everybody else in what I believe will happen. So this is IBM's roadmap. So this is what they actually intend to build. And they've started 2 projects to do this, one of which is aimed to complete in 2029, another one they're targeting 2033. Now, they're just targets, but a serious company with serious expertise has gone out in public saying they believe they can meet these targets. Now, this slide has another thing which I need to explain. And this goes back to what I was talking about, the Giotto spacecraft that intercepted Halley's Comet, and how do you get information back from it and make sure that your signal is good enough when it gets to ground that you can recover what was actually measured deep in space. Now, the thing is that qubits are subject to interference. And within a quantum computer, you're creating that interference deliberately and seeing what happens. But the outside world could also interfere with quantum systems. And this happens all the time. And it's why, despite the fact that these small things behave so weirdly, that the big things, which are mere groupings of the little things, behave in the natural, expected way that we see them. So a quantum computer has got to be separated from its surroundings. I alluded to this before, because if it's not, then there's going to be interference. And you can't do this absolutely reliably. It's got to be thermally insulated, so there's no heat flowing from or to, more likely to, the quantum computer, not even the tiniest amount, and also no mechanical work, no energy mechanically is transferred into or out of the quantum computer. And again, it's going to be into in practice. And that means that you've got to eliminate even the tiniest of vibrations. And this is why quantum computers and their housings are so big, because this isolation has got to occur. Now, it can't be done perfectly, which means that for any one logical qubit, which you're going to use to, in the end, represent either a 0 or a 1, you need many, many physical qubits. And you look at the results that you get from all of the qubits, and you decide that if you have 50 qubits, 50 physical qubits, and 30 of them say 1, and 20 of them say 0, then 1 is probably the correct answer, okay? And the state of the art is that you do need about 50 physical qubits to represent every logical qubit. And the state of the art was actually published in June this year by IBM. Before that, hundreds of qubits physical qubits were needed in order to get one logical qubit. It's now down to 50. So these predictions made by IBM are talking about how many logical qubits they need in order to break, we won't get there. How many logical qubits they will have in those computers in 2029 and 2033. So if there's 200, then multiplying by 50, there's maybe 10,000 qubits that they'll produce. Bearing in mind we're at 1,000 today, so they're looking for an order of magnitude change by 2029, which is less than 4 years away. And for Project Blue Jay, then they're looking at 2,000 logical qubits. Now, maybe you multiply this number by 50 to get how many physical qubits, but maybe by then the methods to separate your quantum computer at the core of it from the outside world may have improved. So maybe you'll only need 30 or 20 or 10. I can't say, but it's obviously going to improve to some degree between now and 2033. And I think this image was generated by IBM using AI, but that's what they imagine one of these Blue Jay computers to look like. It's pretty big, yeah. So what does all that mean for cryptanalysis, meaning breaking the cryptography that we use today? So the most popular, but not actually the best, but the most popular because it was first, asymmetric algorithm that we use is RSA. And when RSA first came into being, by the way, I think I was the first person to implement RSA outside of the USA in the early 1980s. And we started off at 512 bits. Now, most systems that are fielded are using 2048 bits. But that's already looking light, even for the development of ordinary Turing computers. You know, we probably should be increasing from that, even without quantum computers. Security is an arms race, yeah. The bad guys get better tools and better methods, and we've got to keep ahead of them. By a number of years, at least 10 is a good starting point. Now, the information on this slide, the years, 2019 and 2025, are when these academic papers were published. So they're not kind of about the present day necessarily, they're just about when the information was published. So back in 29, this fellow Gibney reckoned that you'd need a quantum computer with 20 million qubits, that's physical qubits, in order to break 2048-bit RSA in about, or a little less than, 8 hours. His work this year, published in January this year, I really don't know why he didn't use the same time frame here as here, but it's indicating that a machine with just 1 million noisy qubits, I say just, it's obviously beyond what we can do today, but 1 million noisy qubits would break 2048-bit RSA. So why the difference between his work in 2019 and 2025? And fundamentally, it's because engineers got better at software, okay? So the mathematical algorithm to break RSA with a quantum computer is called Shor's algorithm. That's S-H-O-R. And it's been known for a very long time. Well, seems like quite a long time, since the mid-1990s, I think. And when it was first implemented to break kind of tiny and useless keys, but just to kind of test the algorithm, then that mathematical algorithm had to be converted to software to run a computer, to run a quantum computer. Now, because a quantum computer is so very different to all the other computers, the Turing computers, software in a quantum computer sense is different to software in a Turing computer sense. So at the beginning, people weren't very good at it, but they have improved. So that reduction from 20 million qubits to 1 million qubits has been caused by engineers getting better at writing software or designing software for a quantum computer. And one may expect that that process will continue. Maybe not at the same rate, but people aren't going to get any worse. They'll probably get better. Now, the 2025 paper, that was January 2025, the IBM breakthrough, which says now we only need 50 physical qubits for a logical qubit, happened in June 2025. So it's likely that that 1 million noisy qubits, an addendum to his paper will be published soon, which maybe takes that down to 250,000 qubits. So that's kind of overnight, really, that estimate will have dropped from a little less than 1 million to maybe less than 300,000. And who is to say that engineers won't get better at isolating all the noise from a quantum computer, meaning that 50 might become 40 or 30, okay? So all these trends are improvements which mean that a viable quantum computer, in order to crack the cryptography that we're actually using, may be ready sooner than many people think. But I will say, the more qubits you have, the bigger your little quantum computer, then the harder it is to separate from the rest of the world and reduce the interference from it. So maybe that improvement from 50, to 40 or 30, it may be not so quick. But it will happen in steps, okay? There will be breakthroughs. And, there are about 10 organizations that are very actively and seriously and backed with lots of money that are producing quantum computers. And obviously, they're trying to leapfrog each other. So, yeah, there will be improvements, but lots of engineering difficulties along the way. So, yeah, I mentioned this point already. Quantum computers are different. They're not better computers, okay? They can solve certain problems better than our present computers. But you're not going to use them for everything. Quantum coherence can only be maintained by stricter isolation we've dealt with. Yeah, the other interesting thing is that Moore's law. Who's familiar with Moore's law? Not very many people. So Moore's law, Gordon Moore was the CEO of Intel. For many decades, the largest chip manufacturer in the world. And way back in the 1960s, he predicted that the capability of microprocessor chips would double every 18 months or so. That's in terms of speed and power consumption, double. But that also, and at the same time, the price of such a chip would halve, okay? So if you kind of double the performance and halve the cost, that's a 4 times improvement in cost effectiveness. Excuse me. Now, amazingly, that turned out to be pretty accurate until very recently. We may be getting to the end of where Moore's law applies, but for generation after generation after generation of microprocessors, it has applied. Now, one of the reasons that it has applied, the main reason that it has applied, is that manufacturers have got better at etching circuits onto silicon more and more densely, okay? The circuits are closer and closer together. Until now, we're at nanometer scale, 1/1000th of a meter, which is actually kind of pretty well down to quantum sizes. So there's nowhere else to go in terms of size. So Moore's law will probably not apply to our microprocessors for very much longer, but also it won't apply to quantum computers, because a quantum computer, by definition, is already at quantum scale. You can't make it smaller. So there will be engineering improvements of one sort or of another. But they're not likely to be this exponential improvement that Moore's law has implied. They will come in step changes, and they'll be small step changes, probably. Right, what does all this mean? Yeah, a quantum computer is not going to be in the iPhone that you buy in 10 years' time, okay? I'm sure your computers, your phones vibrate quite a lot just to let you know somebody's calling, and that will interfere with a quantum processor. So it's not going to be like that. They're not going to be replacing what we already have. It'll be an additional thing. So to use a quantum computer, my guess is, I think most people's guess is, that they will be used from your laptop computer, workstation, perhaps even your tablet or phone, over the internet to a facility where there is a quantum computer that will be used on a time-sharing basis. So what does that mean? So there's not going to be that many of them. I mean, I kind of hesitate because the whole course of computing has been fraught with predictions that have turned out to be ridiculous. So Thomas Watson, the president of IBM, said in 1943 that he foresaw a world market for 5 computers. Okay, so turned out to be completely wrong. Ken Olsen, who was CEO and founder of Digital Equipment Corporation, which during the 70s and 80s was one of the biggest computer manufacturers in the world, eventually taken over by Compaq, I believe, in the late 80s. He said in 1977 that he could see no reason why anybody would want a computer in their home, right? Apple computer was founded in 1976, so Apple already existed, and Ken Olsen, CEO of one of the biggest computer manufacturers in the world, said there's no use for these things in the home. So how wrong could he be? I'm making a prediction akin to those of Thomas Watson and Ken Olsen, because I'm saying there are not going to be that many quantum computers in our careers. I've got very little of my career left to go. Some people in the room will have a couple of decades longer. But I think the point is that they, I think, will be confined to specialist facilities. Okay? And you know, they'll be available, but they'll be accessed in the way that I mentioned. So a lot is going to depend on where those are and how well they're run. Okay? You know, ideally, all of us who are good guys, and we're all good guys in this room, don't want any bad guys having access to a quantum computer. In reality, we have no choice about that. So where will the bad guys be accessing their quantum computers? So they're going to be run by probably pretty large organized crime groups, or maybe, not maybe, they will be run by hostile governments. And there is an undeclared war going on right now, an undeclared world war, where states are interfering in the running of computers and also the cryptography that's protecting things. It's happening back and forth. So in your analyses of, you know, where are we going to look for the bad actors coming from, and James touched on this as well, you're going to need to have in your heads that it could be foreign governments that want to do this to us, and you need to be able to protect yourselves. Now, a well-informed and well-organized and well-run organization that offers their quantum computer for time sharing ought to be able to see what you're using it for. Okay, they can observe what you're going to do. So good institutions in a well-regulated environment will keep out the bad guys, or they will try very hard to keep out the bad guys, and hopefully, mostly, they will succeed. But even, let's say, in a good country, and somebody who, you know, kind of means well, but doesn't think about how their quantum computer might be misused, or maybe they're subject, the operators, the individuals, to bribery, blackmail, etc., then, you know, maybe one of those quantum computers can be used by the bad guys to do the key cracking. What they won't be doing is, like they do now, to use social engineering or Trojan horses to get software embedded in millions of computers around the world that is using spare cycles to crack keys, because there just won't be that many quantum computers to do it with. So that kind of helps. Right, so what to do about it? People have been working on quantum-resistant algorithms, but not for very long. So RSA, for example, was invented in 1976, or at least it was reinvented in 1976 by Rivest, Shamir, and Edelman, hence the RSA. Actually, it had been invented in the UK in the government communications headquarters in about 1970, or a very similar algorithm. And recently released government papers has proved that actually they got there first, before R.S. and A., who were working in American universities. But whatever, it's been around for a long time, 50 plus years. People have been working on these algorithms for a lot less. They were kind of, some of them, known about, postulated, even implemented, theoretically and for fun, you know, maybe 15, 20 years ago. But they've only been analyzed really, really seriously in the last 10 years or so, which means that they're probably good, but they may not be. Somebody may be working right now, either openly or secretly, on ways of subverting these algorithms, and they may be successful. And what that means for us, I think, is that cryptography has been a relatively stable subject for as long as I've been working in it, which is 40 years. So yes, we've needed to move from 512-bit RSA to 1024-bit to 2048, and we ought to get to 3000 and something quite soon. But it's still RSA. It's still the same algorithm. The principles are the same. So when we as organizations running large networks or advising people who are running large networks, we kind of understand what we're doing in increasing a key length. It's not that hard to understand. And everything else that goes around that cryptography still ought to fit. It's not quite plug and play, but it sort of is. People, by the way, are still reluctant to change. We've seen this in EMV where, you know, there's an AES migration that EMV, you know, have been pushing for 10 years, but I don't think any large scheme has actually implemented it yet. We know some that are working on it. So it does take time. So these algorithms that I've highlighted, they have been made US standards for commercial transactions by an organization called NIST, which is the National Institution for Standards and Technology. And they've been working on huge numbers of standards for secure computing for a very long time. They're a very professional organization. They're open about everything they do. They run intensive tests on new algorithms. They recruit academics from around the world to help them with that. So if you're going to start anywhere, you would start with NIST. Now, that's one reason for starting with them, that they spend a lot of time to evaluate algorithms. Another reason is that other people will too. And I think this is particularly important when we're talking about retail transactions, the front end of a retail transaction. Because increasingly, and I've seen some demonstrations outside, we're relying on mobile phones, not just for the consumers, but also for the merchants, increasingly to do the transactions. So ideally, you want to choose a cryptographic algorithm that the manufacturer or the operating system provider has already embedded in that phone. And they're going to look here, because we're talking Apple and Google and Samsung, okay? That's where they're going to be looking. So if you want to save yourself some work, because you don't have to go out and find, you know, some software shop somewhere that's implemented an algorithm, but maybe has not really tested it that well, you want to go here and rely on stuff that's embedded in the equipment that you're going to be using, your customers, and your customers' customers are going to be using. Also, those algorithms embedded in the mobile phone are going to have access to the most secure spaces within that phone. So embedded secure elements, secure enclaves, trusted execution environments. The cryptography is going to live there, so it's going to be quite safe. If you do your own thing, then you're not necessarily going to have access to those secure areas. And if you do, probably other people will as well, and that will maybe raise alarms as to whether it's genuinely going to be secure for you. So if you have to use the host processor in a mobile phone, then you have to cycle keys really, really quickly so that the attacker doesn't have time to use a key that he's cracked before you've replaced it, okay? And that latest example I gave about the state of the art in how many qubits you need suggests that, you know, it was less than a week, it was said. So you would definitely want to change your RSA keys in less than a week. For quantum-resistant algorithms, it wouldn't be so much, except, you know, if you haven't got a safe place to store the private key, then you are in trouble and you need to cycle quickly, and these keys are kind of big. So over here, we're looking at key length and the size of cryptograms. And unfortunately, this is bad news. So the kind of best current asymmetric algorithms are called elliptic curve cryptography, ECC. And elliptic curves were kind of worked on a bit after RSA, and they kind of, by moving from RSA to elliptic curve, you kind of get away from this continually having, or every 10 years or so, having to increase the length of keys. And besides the operational issue of changing from one algorithm to another, elliptic curves are better in every respect to RSA. So they have smaller keys, which are easier, therefore, to handle. And they have smaller signatures, which take up less space to transmit, so you can get things done quicker. With the currently known or standardized, and actually there are lots of other algorithms quantum resistant besides these. All of them, you have to make sacrifices in terms of either key length or the size of the cryptogram, and actually probably both. And you want to find some optimum. Now, we've been doing a study for the National Rail Supervisory Organization in the UK. There are lots of different train operating companies in the UK and lots of retailers who can sell you a ticket, which is a barcode ticket. And currently, those barcodes do contain a digital signature, which is formed by 1024-bit RSA. Now, they need to update those barcodes anyway, because the system is going to be extended to buses and other forms of transport throughout the UK, which means they need to store more data. If they're going to change those QR codes, they should look at changing the cryptography as well. And so the question is, do you go to elliptic curve? And elliptic curve, by the way, is vulnerable, just like RSA, to quantum computers. Do we use ECC for now, or do we go straight to a quantum-resistant algorithm? And which quantum-resistant algorithm? It was kind of obvious which one to use, and it's not one of these, because the signatures are all too long to fit in a QR code that's not going to be so detailed that it can't be read accurately at a gate at a railway station to move through quickly while there are 10 impatient people behind you. So none of those would work in that situation. So we chose another one to study, and we haven't concluded that process yet. But the important thing to note is that moving to a quantum-resistant algorithm will not be without sacrifice. And it also means that you have to plan very carefully, because maybe having a longer signature means that a transaction is too slow. Maybe having longer keys means that some people don't have enough storage to store all of the public keys that they might need to play their part in a service. So it's not, yeah, quantum computers are coming, it makes sense to move next week or next year to a quantum-resistant algorithm. It's going to take a lot of planning. I want to point to one other word on here, and that's this word, backup. So this algorithm is designed to do exactly the same business function as this algorithm, the one above. And it's there for two reasons. One, because it has different properties, and in particular, the key length is looking pretty good. Signature's looking pretty bad, but it gives a choice. But it's also there for backup purposes in case this algorithm is cracked. which says to you that NIST, which has done more study on these algorithms almost certainly than any other organizations in the civil sphere anywhere in the world, they're not really sure. They've made it a standard, this one, FIPS 204, but they think they need a backup. Now, my hunch is that because the cryptographic world has been relatively stable for a long time, we've got into a certain way of working, but we're going to have to change that. We're going to have to be more agile. And the advent of quantum computers may mean that we'll have to change algorithms more frequently than we've been used to. So that means that not only have you got to plan one process very carefully, if you need to be quantum resistant, but you're going to need to come up with a repeatable process that you can take the manual off the shelf and run the process again. Let's say in 5 years' time or 3 years' time, but you may not get much notice because algorithms get broken with breakthroughs that happen all of a sudden. So even if you don't plan on moving to a quantum-resistant algorithm soon, you are going to need a process, I think, that is not just a one-off, it's a repeatable process. So, how much time do I have left? Not very much, so I'll try to go through this quite quickly. This is our approach that we have been discussing with very many national payment schemes, particularly in this region, but also in others. And we're getting good traction with a number of organizations who have indicated that they would like to follow this method or something quite close to it. So what are our objectives is, first of all, to build this repeatable methodology. And it's going to be in 4 steps, so I won't kind of read what's here because we'll get into a little more detail later. We've got to ensure that we do this in time, and it has to be scalable because you're talking here about systems that cover a massive country, I think the 4th biggest population in the world. There's also scattered all over the place, all these islands, and with thousands of banks, tens or hundreds of thousands of merchants or people who accept payments, 250 million people, or however many it is. And they've all got cryptography in their hands. They've got cryptography in their mobile phones that they're using now to do payments. And it all kind of has to change. So it's a big scale. And we have a complicated ecosystem in payments. All of these people, all of these types of different organizations, banks and merchants, acquirers, issuers, central banks and regulators, everybody has got to be on the same page. And they can be put on the same page by laws and regulation, which we would kind of recommend, provided those laws and regulations are not absolutely static, because as I've just said, you're probably going to need to move again and again, but the right framework ought to be in place. And people have got to come together in forums like this and more formal forums in order to agree what is going to be done. Because unless everybody's doing it, it's not going to work. And I refer to AES migration. AES is a symmetric algorithm, so kind of irrelevant to quantum. But EMV have been trying to migrate for 10 years, not very successfully. And of course, there are lots of stakeholders. They've all got to want to do this. So there's lots of education required. There's lots of knocking heads together to get on the same page, so everybody's thinking in the same way and doing the same thing. So we're talking about current systems that use RSA and ECC. They will probably need to change. We want to talk about a structured approach, a handbook, if you like, for doing this activity. And what will be gained by it is a clear understanding, not just at a technical level, but a business level as well, about what the implications are and what a high-level plan looks like. Producing a high-level roadmap is part of the process. Right, I don't expect you to read this. Hopefully this presentation can be made available. But if you just concentrate on the two diagrams, and I'll explain at a high level what they are. Right, this is barely readable. There's another slide that this is the four-step process. So I'll explain what each of these steps are in the next slide. This is stakeholder engagement. So as I've just been saying, all of the stakeholders have to be at the center of this process. This diagram is indicating that the process needs to be repeated. So the threats to your services are not going to be static. Your own services, what business functions they perform and what technology they're going to use will change. And the outside world will change in terms of technology as well. So you do this analysis in year one, and then you repeat it in year two, year three, etc. It doesn't have to be a year, maybe 18 months is the right answer. But the crucial thing is the kind of hard work happens in year one, and the repeat functions are deltas on what you've already come up with to take account of changes. Right, so the four steps, and I'll go through this really quickly. The first is an audit, right? Understanding what cryptography you have. And now I can guarantee that you could bring your technical teams into this room, and I could ask them, where are you using cryptographic keys today? And I would look at one single individual. They might be the head of cryptographic security, but that person will not know every single key type that's in operation throughout the system in order to conduct, for example, a single retail payment. They just won't, because there will be hundreds of different types of keys that are in use in different places, so in different domains, be it the merchant domain, the acquirer domain, issuer domain, blah, blah, blah. They'll be in different places. They'll be at different level of the technical stack, from physical items of equipment, protected communications between them, up to TSL communications across the internet, and then at your application level. And there's also a supply chain. In order to get all of this working securely, you need software that is well understood and which hasn't been interfered with. And supply chains are increasingly more complex. And you need to know that modules of software and hardware that have moved from one organization to another, where they've been integrated with something else, then onto a third organization, more integration, and eventually it gets to a merchant, and it's his point of sale equipment on his desk. You need to understand where cryptography is used in that supply chain. So doing the initial audit is kind of harder than it looks. Next, we have a methodology that we've been using in Consult Hyperion for 30 plus years. And I'll go on to the next slide to do a little bit of explanation about what it is. But it will help you to understand, of all those hundreds of different keys, where do you need to change algorithms? It will help you to understand that. We need to understand, and obviously this is where we can help, what the current scientific technical literature is saying about where we are and where we're going to, which I've been through with you a bit today, but it changes, so we need to keep up to date. And finally, we need a plan to work out what on earth we're going to do about it all. And you need that plan, and out of that plan, a number of projects may spawn, because it may be there are some areas that are critical and might be exposed sooner rather than later because they're protecting very valuable assets, for example, or they're protecting a lot of assets. But to change everything at once would be an impossibly difficult project, so we need to understand what's critical and what's not. Right, this is just a slide to say for every type of key, and like I say, there's probably going to be hundreds. What are the characteristics of how it's used? What's it called? What key length? What algorithm? What service is it protecting? What layer of the stack is it? Who looks after it? Where it's generated? Is there a certification authority? Who's that? What it's used for? How long is it planned to last? So that sort of information about every type of key that's in your systems, plural, you're going to need to understand. This is our structured risk analysis methodology. I kind of invented this methodology 35 years ago, so I could speak for 45 minutes on it. I'll try and keep it to 45 seconds. The key attribute of this methodology is that it separates business concerns from technical concerns. So over here, these purple blobs, they're to do with business. So how does our system work? What does it do? And what are the threats to the business information that is required in order to do those things? In other words, is this going to be a nice target for the bad guys, or is it going to be something that probably they're not going to care too much about? These orange blobs are looking at the technology. So these two can run in parallel. So when I'm doing, or we are doing the business, we don't need to, with this analysis, to understand what technology is being used at all. In the technology stream, the people doing that analysis don't need to know what it's going to be used for, but they're just looking at the inherent vulnerabilities of those pieces of technology. How easy are they to penetrate? How much would it cost an attacker? What kind of education do they need? What kind of resources? And are they likely to be caught or not? Because that will determine to a large extent whether people will try. If they think they're going to be caught, they probably won't do it. What that comes out with is an assessment of risks when we combine these two analyses together. An ordered set of risks, ordered according to exposure. How much are us good guys exposed to these threats because there are vulnerabilities? And when I talked about you'll need a plan before, but you don't want to do everything at once, how do you decide what to do first? It's on the basis of this analysis. So some risks you will have a great exposure to in the world of quantum computing, so you've got to plan in detail and start to implement those things as soon as possible. Other things can be left. So we need to get on to questions. So I'm just going to wrap up there. The rest of the slides were more detailed on the method. Thank you very much.
Thank you so much, Mr. Neil McEvoy, for the comprehensive presentation. Because of the limitation time that we have for this session, we cannot have the Q&A session. But hopefully during lunchtime, if you have a spare time, the rest of the delegation and have a Q&A directly to you.
Okay.
Thank you so much once again, ladies and gentlemen. Please give a big round of applause for our speaker. Bapak dan Ibu, kita sejenak melihat ke layar di depan karena kami juga sudah merangkumkan apa yang menjadi sari dari presentasi Mr. Neil McEvoy di sesi ini. Dan terima kasih atas bantuan teknologi, kami sudah merangkumkannya dengan bantuan Artificial Intelligence, di mana kita diajak untuk memahami aspek dasar dari mekanika kuantum dan juga komputer kuantum. Di sini tadi Mr. Niels McEvoy juga menjelaskan bagaimana prediksi masa depan komputasi kuantum dan juga dampak potensialnya. Di antaranya adalah analisis kriptografi. Ada juga faktor dari mitigasi potensial dan juga quantum resistant algorithm yang bisa kita pelajari. Kemudian pendekatan ketahanan yang juga diusulkan diantaranya adalah kerangka kerja tangguh yang aman terhadap kuantum, mitigasi risiko yang tepat waktu dan juga dapat diskalakan. Kemudian tentu ada juga penyelarasan para pemangku kepentingan dan juga penguatan posisi-posisi strategis. Kemudian penjelasan mengenai mitigasi kesiapan kuantum diantaranya melingkupi audit layanan kripto, analisis risiko terstruktur, tinjauan literatur dan juga perencanaan implementasi. Dan juga dibutuhkan pendekatan kolaboratif dengan melibatkan seluruh pemangku kepentingan antara pemerintah dan juga SRO atau Self-Regulatory Organization serta pelaku industri. Bapak dan Ibu yang juga semakin menarik jika presentasi ini bisa kita visualkan. Untuk itu saya mengajak Anda melihat inilah dia visual dari Artificial Intelligence merangkumkan sesi kedua kita hari ini. Dan sampai jumpa di sesi panel discussion setelah makan siang.